So now we're moving into the final stretches of the Atom Probe workshop. And what we're now going to do is we're going to look into local proxigrams and into concentration mapping. And concentration mapping, well, local proxigrams, I think, are relatively self-explanatory. It just means you do a proxigram, but you don't do it from the entire interface that you've defined, but you're doing it from a subset of the interface. Yeah. So you're going to have a way to choose a subset of the interface. For concentration mapping is essentially similar or the same as a 2D concentration map that you're all familiar with, but on an object that's curved. Yeah? It doesn't need to be flat. And you know, most objects in atom probe tomography data are actually curved. Yeah? So that's pretty much the natural shape that atom probe objects have anyway. And if you want to read up on the fundamentals, we're going to go through them anyway. There is there should be I did write a paper once about that. I'm pretty sure I can find that. Oh yeah, there we go. And of course I don't have access to my own paper. Great. But it's on my computer over there. I'll pull it up. I'll pull it up in the afternoon then, in the later session. Anyway, many of you, if you just Google local proximity histograms and atom probe, maybe we can sneak in and anyway, I'll have to explain it anyway. So the question now is, okay, we can make proximity histograms relative to 1D, 2D, 3D, 0D, 1D, 2D objects. Obviously, relative to 3D objects, it doesn't make any sense in 3D. We could do it in 4D. If you've got some time series, not in atom probe, but maybe if you do it in synchrotron tomography, where you have time series, you can do a proxigram in 3D. So the question is, how can we become local? Yeah, how can we pick an area of on the interface that we want to analyze? And I'll just make a little sketch about that. And it's actually pretty intimately connected mathematically to what we've been doing so far. Yeah. So just imagine again that we have some kind of interface, that consists of in 2D edges and vertices, and it looks at least somewhat nice. Yeah, it looks at least somewhat nice. And now, maybe a lot of atoms here. We don't have as many atoms here. Yeah. This is something that can definitely happen. So the question is now, if we plot, what colors did I use before? If I plot, if these are my surface normals, if I plot concentration versus distance d, does it make all too much sense if I do it for the entire data set? Or would it make more sense if I do two proxigrams, maybe one for here and one maybe for somewhere else? And the way to do that is actually to select which vertices, or to select the area by selecting which area on the surface I want to work on. And the way that works is actually the way that the proxigram that we looked at has always worked, and maybe I haven't shown that all that clearly, is that when we're doing a distance calculation, we allocate each atom to the closest vertex anyway, because we say, okay, we need to work along this surface normal, so we know which vertex each atom is the closest to. what that amounts to is actually a so-called Voronoi decomposition. So again, we've got our Voronoi cells. Yeah. In this case, the Voronoi cells, since we're looking from the side, yeah, the Voronoi cells would look something like this. Yeah. So what I can go is actually I can view each of these sub-volumes here, each of those Voronoi cells. I can see as a Voronoi cell belonging to, maybe this is vertex 1, 2, 3, 4, 5, 6. Yeah? And what I want to do is I want to create a proxigram, for example, where I take the subvolumes of vertex 3, 4, and 5 maybe. Yeah? And then maybe a separate one for 1, 2, and 6. So the question is, of course, how do I pick first where, if it makes sense, if there's a difference, if it makes sense to do that. And the next question is then, well, how do I find the individual vertices, or how do I mark them for analysis? Yeah? But it's this Voronoi decomposition that's actually the core of everything. It's not necessarily an explicit one. Explicit one would mean we calculate geometrically what the Voronoi cells are, and then do a containment test to calculate which atoms are inside the Voronoi cell and which ones are not. You can do that, but that's computationally fairly expensive. The much simpler way is the implicit one, by just saying, okay, this atom is closer to this vertex than to any other vertex. Okay, and this is really the basis of our analysis in this case. And of course, you can use it to do concentration mapping as well, because just like before, you could just say, okay, I want all of the atoms that are within a certain distance of this interface, yeah? And then I might want to calculate the concentration for those. You could have done that, by the way, with our voxelization just earlier. Yeah? That's not a big problem, because we can use the distance to the closest vertex as one coordinate, and the vertex number as one coordinate. The reason why that is not super practical is because unless you have an extremely flat surface where you can just have a rectangular interface thing that you put in, the vertex indices of neighboring vertices are not necessarily in incrementing order. Yeah? I mean, that's just not possible in 2D, and even less so in curved 2D. Yeah? So anyway, this is the basis of everything. And let's get cracking with that. And I think the first thing we're going to do is to calculate a 2D concentration map, yeah, which will then give us an idea of where we would look for higher or lower concentrations. Yeah. And if you remember right, we've already calculated an isosurface, yeah, and we are going to go and pick one individual isosurface to do that. For this data set, I'm not quite sure if there's too much uneven segregation going on. So I've got another one that's a nanocrystalline duplex steel, and that we might pull in later because there are actual concentration differences on the interface. Okay, so let's get started. So let's go and pick one individual interface, and we already have our decomposition. We already have our patch to OBJs. So we have the individual OBJs, and I'll show you how to do that in Blender, which is really easy. You already know that, yeah. So you could just go and pick one of them and then export it as an individual OBJ. Yeah. So this is pretty simple, but we can also do that inside of MATLAB. Yeah. And well, I haven't moved over yet. Yet now. So you could do that in Blender. You can just click on one of them and then go File, Export Wavefront, and then just go Selection Only. Yeah. Of course, Y forward, Z up, and then we'll just re-export that. But you don't need to do the extra loop. Yeah. You don't need to do the extra loop unless you have a reason for it. You want to work on your objects, for example. And the simplest thing is just to plot them individually, and then I'll show you our Isosurface app that we have, so you can do that in the app as well. And that's actually super simple. Okay, so the first thing we're going to do is we're just going to create a color variable which just creates a random color for each object. Yeah, and I'll just name that colors, and that's just a random matrix, and we have a certain number of patches, a certain number of objects in there, so that's our FVs. Yeah, and we need RGB colors. Yeah, so there are three entries per thing, and all that is just essentially a matrix of random numbers that is 25 times 3. Yeah, and so what we can then do is take what I've done earlier the wrong way around. Why has my MATLAB become so slow? I might just reopen MATLAB then. After we've done that, I might just reopen MATLAB because we're just going to start from scratch. With the Isosurface app, everything goes pretty fast anyway. So the face color, now we're just going to go and use colors P and all entries. And our variable is called FVs and not FV. And that should do the trick. And that didn't do the trick, and the reason was I've only plotted the latest one. So we need to go and say hold. Okay. Did it now finally really freeze? That would be bad. Okay, so for hold on, so that it doesn't remove the old plots, and end. My bad. Because we want the piece object to appear. And we're gonna need to restart MATLAB. I have no idea what went wrong there. Maybe it's because we still have the extremely large variables open here. Oh. And there we go. Yeah, we're just going to APT via our axes. And then you can see each individual one has an individual color. And we can go and select individual isosurfaces. Can go and select individual isosurfaces. And then I could go the selected one is then our current object, for example, GCO, just like we've used before. And then we have our new variable called ISO, which is just a link to the to this patch object. And from this From this ISO object, you can pull out the vertices, vertex normals, faces, and so on and so forth. Yeah. So all of the data that we need for analysis, that's all contained here. And let me just delete the largest. And see if it becomes more responsive again. Okay, now it's happy again. So always make sure that you have a computer with enough RAM. So we did voxelize quite a large data set. Anyway, just make sure you have enough RAM. Okay, so now it should work fine again, and we are now going to just open our okay, why is it separate here? Our Isosurface Widget app. Yeah. So we're going to open our Isosurface Widget, and in the Isosurface Widget, let me just maybe copy all of the other stuff, the visualization into here. And in this case, we want to have we want to know what the concentration of hafnium, carbon, and boron is at the voxel size of 2 with a certain color scheme relative to silicon. And I, honest to God, have to look up which one is which, but we can obviously open all of that so that we can look into what order the inputs are. So we can go into the code view and startup function, and we have pos, numerator, denominator, bin size, color scheme, and you optionally can plot into a certain axis. Yeah? So you might want to plot those isosurfaces that you create into, I don't know, an axis where you're already visualizing some atoms. So you can do that. That's not a problem at all. Okay, and I think you can use all. Can you use all? Well, we're going to see. Anyway, so I think so. Which way around was it? Numerator, denominator. Numerator, denominator, bin size, color scheme. Yeah. So the numerator, in this case, we want aluminium, and we want aluminium with respect to all of the elements we have in there. And I'm fairly sure you can use all. If not, we will definitely implement that. Oh, we need to load the color scheme. Okay, we will definitely implement that. So we're just gonna use nickel as a numerator then. Probably chromium is also good. Because chromium doesn't go into the Okay, that's not all that good. Histogram count must be. But we have our pos file, that's all good. Martina, maybe you have an idea of what I'm doing wrong?
Hi, actually, no, but you could open the workflow Isosurface because there it's well designed or scripted what you need and which order you have to put it.
That is a very good idea. Oh, and instead of all, you can just go categories pos.atom, because the categorical array, and then you get all of them. That's why all doesn't exist. My bad. Okay, Isosurface workflow, Isosurface. Okay, visualization, Isosurface Widget app. So here we want everything. So categories. So all categories of pos.atom. The species we want to look at is aluminium. We want to have a bin size of 3-4 nanometers, something like that. And we have the color scheme and the Isosurface widget. Okay, and we don't have a plot axis, or do we need one? No, we don't need one. That's optional. Okay, now it's calculating, so whatever I did, I did it wrong. Anyway, that's why Martina has made these nice workflows. And
I think you have to run the Isosurface widget line code in your command line. That's why it was green also, so uncommented, because it doesn't work inside the work.
Oh, because then the because it tries to plot into the figure here. Ah, yeah, I understand.
Yes.
Okay. Probably it says it in the text.
Yes, Peter, it definitely says it in the text.
Okay. So now here we have one figure that shows us our isosurface, and here we've got a slider that gives us the ability to drag the slider to certain ISO values. And we have a histogram of concentrations, and if you have two different types of volumes, then it's probably a good idea. Probably a good idea to drag the slider just essentially right smack bang in the middle. And I think if you look at the isosurface, you'll understand that that's probably not a bad idea generally. Yeah. So that's something that gives us a pretty good partitioning. And you can see the color is already from the color scheme, the color for aluminium that we're using. Yeah. I can change the color if I want to. So I can click on change color and make it, I don't know, whatever color this is, purpley color. And I can filter by patch size. So I can go filter by patch size, and then all of the small patches will be gone. All of the small patches will be gone, and we're left with the ones that we probably actually care about. By the way, if you drag the slider again, everything will reset. Because a new isosurface is calculated. Anyway, so I'll filter the patch size. Maybe 100 was a pretty of a strict filter, because there's a precipitate right at the top that apparently has less than 100. So maybe we'll use, I don't know, 25. Filter patch size. And now we still have it. And we can then press split surfaces. Yeah, and then it creates a then it splits all the individual surfaces with individual colors. And now what I can do is I can select certain surfaces. I can select this surface, I can select this surface, or I can select more than one surface. And what's going to happen is, I'll just select those two. And if I now go create variable, it dumped all of the information into the it dumped all of the information to the workspace. So we've got 23 isosurfaces that are big enough. We've got all of them here. And we've got an additional variable that tells us which ones are selected. Yeah. In this case, it's isosurface 12 and 13. Yeah. So this way we can actually easily find out which individual isosurfaces we have selected. I'll just close that one. Which individual isosurface we have selected, and in this case, I don't know. Maybe I'll just select this one, and that's what we're going to use for further mapping analysis. So let me just click on that isosurface and then get back to the isosurface widget and go create variable. And now if I look into that variable, there should only be one selected, and it's the number 12. Obviously it's logical indexing, so I can just go fv equals isosurf blah whatever. In this information it actually says okay, the concentration is 0.075, because it works for all kinds of ISO values. Yeah, so 7.5% in this case. And we can just select the ones we want to select by go find isosurface selection. Yeah, this just gives us the indices of the selected isosurfaces. In this case, it's just one. Yeah, so we have one isosurface here. We've got one isosurface here, and we can very easily do a proxigram. We can go bin centers, bin edges, dist, pos distance to mesh, or pos versus this variable fv, this interface fv, this one interface from the isosurface that we have selected. Yeah, obviously now we're dividing up a very large data set into individual pieces. Yeah, so the distance calculation takes a little bit longer. But I've done that on isosurfaces or on data sets with 100 and 200 million ion count as well. And you might just need to wait a couple of seconds. Okay, so we've got that one here, and then we can go and calculate our bin edges and bin centers. That obviously goes pretty fast. And even for a large data set, if you just do one-dimensional binning, it shouldn't take too long either. So our visualization is pos nd bin. And we are binning across bin.distance and bin.edges. Or you can just use the proxigam program. But since we already started using the ND binning, I'm using the ND binning right now. And now we can calculate the concentration. Spin, I think CK still exists. Yeah, the anonymous function still exists. So we've calculated the concentrations, and then we can do a concentration plot. In this case, again, probably nickel we're not going to use. It's also superalloy. Now, And there we go. We've calculated a proxigram relative to that one interface. Obviously, probably only values close to that interface make a lot of sense, because once you move further away from this one interface, yeah, you're going to move into other precipitates and whatnot. So, and this is something you see here in the concentration fluctuations. Yeah. And so we might just restrict our view to anything maybe plus minus 10 nanometers within that surface. So we can go axis is get current axis, and axis dot x limits is equals, goes from minus 10 to 10. And now we just have the immediate area around it, around that interface. Yeah. Okay. So we did a proxigram for that individual, for this individual precipitate. But the question is now maybe, can we have a look at the distribution of a certain element on the interface? And maybe that's not the best example here, but anyway, just for demonstration purposes, I'll do it with that, because we don't have anything enriched. Now, if you look at the proxigram, there's nothing really enriched there, so I don't know if concentration mapping really makes all that much sense. But anyway, well, just for demo purpose, do it here, and then we might move on to a data set where there is actually some significant concentration differences on the interface. Okay, and for that we actually have a function, and the function is pos calculate. This is pos patch create to the concentration map. Yeah. So for that, what do we need? We need so we also have density maps and so on and so forth. Yeah, but we'll start with the concentration map for our pos dot atom equals, I don't know, what are we going to use? Aluminium again? I don't know. Yeah, what the hell not. Aluminium, all entries. We want to map that with respect to the entire POS file. The interface that we're using is this isosurface that we picked and we've thrown into the FV variable. And now we need to say, okay, what distance around the interface do we want that concentration map to be calculated? And I'm going to choose a distance of 4 nanometers. And this distance is, I have to look that up, the distance. Yeah, so you can explicitly say you can pass a 2-element vector, then it will go from D to from element, so from maybe minus 2 nanometers up to 3 nanometers, or you can just provide one value, then that's the thickness of the slice where we do that calculation concentration. Did we not properly update that? That's a bit of a fv.vertices pos. That is, I have to apologize, that is a non-updated version of the concentration map program, which is unfortunately meant for the before we use tables to display atom probe datasets. So sorry, we're going to update that, but I'm then just going to show it anyway. So we're going to have just a variable p, which is going to be our pos, and that is going to be the coordinates, just the coordinates. So it's going to be pos dot atom equals aluminium, first entry, so the X entry, pos aluminium dot X dot Y and dot Z. That I really have to apologize for that. I thought I had checked that beforehand. Anyway, now we have a variable p where all the coordinates of the aluminium atoms are in there, and we're gonna use parent pos, and that's just pos dot x, pos dot y, and pos dot z. Again, that goes onto our list of things to fix. Okay, so now we have the coordinates in there, and then we can create our map, and we'll have p parent pos and a thickness of 4 nanometers. And let me just copy all of that into the everything from we will fix that. It will still we will fix it in a way that it will still work with this code as I've demonstrated here, but so that you can just use our newer table-based analysis system as well. And now it's actually doing the whole allocation, the concentration calculation, and so on and so forth. And that will, again, for a large data set like the current one, will take a little while. And then we'll pop up with a figure, showing that concentration map. And I can just close the Isosurface widget. By the way, if you've created a figure like this with the Isosurface widget, it's a standalone figure. So if you close the widget itself, it will just keep existing as a figure. So you can save that, or you can do whatever you want with it. So now, what is the problem with the whole thing, and why might we need to jump in and do some work on the mesh here? Well, while this is calculating, I will just jump over to the tablet again and to our sketch from earlier. So now what we're doing is we are calculating a concentration for here, a concentration for here, a concentration for here, a concentration for here, here, and here. But of course, if you have one of those vertices, or one of those triangles be really small. If you look from, maybe I'll just draw a mesh from looking head on. I might have a mesh like this, and you might locally have some triangles that are, for one reason or another, very small. You might have some very small triangles, and then some of those subvolumes will just be extremely small. So you're not going to have very good statistics there. So it's going to look very noisy. And this is something that's fairly inevitable if you create an isosurface using using the Lorentz and Klein algorithm. And this is sort of the mother of all isosurface algorithms, and all current ones kind of work like that one as well. And it's a so-called marching cubes isosurface. It's a marching cubes isosurface, and the way a marching cubes isosurface works is oops. Oops. I thought it would be easy to copy it in. Anyway, my switch over the presentation. So this is how the marching cubes algorithm, and this is the one that most modern isosurfaces work on. There's some other isosurface algorithms as well, like surface nets and so on and so forth. So the results in. But the way that they work is that you divide your domain into a grid of cubes. Yeah. So just imagine you have a second grid that's overlaid to the first grid. Yeah. So we had our atom probe data set. And our atom probe data set is chopped up into little bits, into little cubes. Yeah. And then we have, for each of those cubes, we have a concentration value. Yeah, so we have a concentration value for here, one for here, one for here, and so on and so forth. Yeah. And the question now is, how do I connect, or how do I find domains with the same value? Yeah, that's what an ISO value is. Or essentially, we are going to give a threshold. If the concentration is larger than threshold, then we want our volume to be outside that surface, and if a concentration is smaller than threshold, or it would be inside, and then it would be outside if it's smaller than that. Yeah? So we have the second grid here, right? The second grid here, and what we do is essentially, if we say, okay, these are the ones that we care about. Yeah, so these are the ones that are good, that we want to outline. So what we're doing is we're putting a surface in between the ones that are below the threshold, the ones that are now the gray crosses, and the ones that are now the red crosses. And we're going to do that in a continuous manner. So we're going to interpolate where the surface is. So if the concentration here at this red point is very close to the threshold, then we want the surface to be very close to here. Obviously, if the threshold is very close to this value, you want it to be very close to here. And so the isosurface that we create in the end will be somewhere in between. It will be maybe here, it will be very close to here it will be a bit further out, and so on and so forth. So we do a linear interpolation. A linear interpolation, and we do that in 3D. So each one of those things is a cube. So there is a finite number of mesh topologies that you can have from that. Finite number. And those are those 15 cube configurations that I was just showing on the Wikipedia page. So here we have in one of those cubes, one value above the threshold, then you need those 3 vertices here. And the other ones are outside. Here we've got 2, then 2 that are sitting on opposite sides, and so on and so forth. And from this, our mesh is built up. But of course, if you have, for example, this situation here, and the threshold value is very close to this vertex value, and this triangle is going to be very close to this vertex, so it's going to be a very, very small triangle. So if I then base my analysis on the location of the individual of the atoms relative to those vertices, and I just say, okay, do the analysis on a per vertex basis, then each one of those vertices is not going to have a lot of atoms associated with it. And this means we're going to get a counting noise essentially. By now, by the way, the concentration map has finished calculating. Obviously, there's not a lot of gradient in there, but we can see, for example, that here, you have some very small triangles, and we might want to get rid of those small triangles in one way or another. And so we are going to work a little bit on that mesh in order to make a bit of a better mesh. So that's one aspect of problems that we can have with isosurface meshes. The other problem actually appears right here, and is so-called pinch points. So what can happen is that essentially just think of this. Oops. Why did it? Just think of a situation where you have a situation like the one here, and then you have where you have a situation like the one here, where you have two opposing vertices being above the threshold, and between none of them are. And if they get close enough to each other, they can sort of one vertex can be inside, whereas the other ones are all outside. And this is what creates these pinch points. And these pinch points are not surfaces anymore at all. They're not really surfaces, because locally a surface needs to have a defined inside and outside. And if a vertex belongs to two surfaces, it doesn't have a defined inside or outside, inside and outside. For a concentration map, we can just say, okay, we don't care all that much because, we're just not going to look at this part of the concentration map. But next thing we're going to do is we're going to make this interface a little bit nicer so that we can use it for better interface meshing. And of course, we can do that in Blender. We'll just load that one object in so that it doesn't get too confusing. So I'm just going to export that, which is patch to OBJ, and we want to export our FV, which again is our current analysis object. And I'm just going to save that into data for isosurface. And I don't know what I'm want to call it. Precipitate 1. It's probably not a good name. You should probably name it something that also tells you what isosurface value that is or iso value that is, and so on and so forth. But for brevity, we'll do it that way, and then we can go and load it into what is screencast keys not on? Screencast keys. Okay. Screencast keys. Okay. So we're going to go file, import wavefront, OBJ, and we're going to load in our precipitate 1, Y forward, Z up. So that's all good. Why are the screencast keys not on? I activated them. Do you actually need to have... Okay, I just leave that open. Okay, so what can we do in order to get rid of those small triangles? And I'll just put on the visualization so that you can see what individual triangles are. And there's a bunch of ways where we can do that. Viewport display, and we want the wireframe. And you can see this is this is not the nicest. Here we've got a very small triangle, and here we've got some other small triangles we're going to get rid of. And the easiest way to start with is to, and I'll just make a copy, Shift D for duplicate. Oops, and I shouldn't have moved it, because we want to keep it at the same space, at the same spot. Shift D, enter, without moving it. I'll just make that one invisible, just so we have a copy. And we're gonna go into edit mode, and we're going to go remove doubles. Okay, and that's probably moved to somewhere here as well. Okay, let me just change something about the preferences again. Interface, viewport. Navigations. Key map, 3D view. Because it used to be that hitting the space bar was not playing back the animation, which we don't have any animations, but it used to be searching for a command. Okay, let me just Google that. It's F3 now, okay? F3. And we wanna, okay, we should mark all vertices, F3, and go remove So where's remove doubles gone? Mesh, cleanup, merge by distance. Oh, it's called something else now, okay? Mesh, there's a new cleanup section. That's actually good. Oh yeah, so you can find all of the operators for mesh cleanup here. That's good. And we'll have split non-planar faces, split oh, that's pretty nice actually. So maybe I shouldn't complain. So we go merge by distance. Yeah. And here you can then increase the distance. Yeah. And as you increase the distance, more and more of the smaller faces go away. Obviously, if you go to very large distances, almost all of them go away and your isosurface is probably no longer recognizable. But if you go to something that's kind of like the half of what the vertex, the distance was, then you're not actually removing any information. Yeah. So we're just going to use that. So we're going to use 1.5. Yeah. Going to use 1.5. And that actually gets rid of all the small triangles for us. Yeah. And so let's move out of that, and we can now compare that to the original. And you can see the actual distance. Yeah? So the actual, if we go into isosurface distance, the surfaces are still fairly identical. They're still fairly identical, but this one is just a much cleaner mesh. This is just a much cleaner mesh. Okay, so this is one way of doing it. Then you could also do it using modifiers. So you can have modifiers, and you can do something that's called remesh. Yeah. So where's the remesh modifier? So it's the remesh, which is actually a that's where's my we don't want that, and we don't want extremely small voxels. We want larger voxels, and we want smooth. This is actually, ironically, this is using an isosurface on an isosurface. Yeah. And if I compare that with the other mesh, you can see it's a little bit different. Yeah. So it's not quite exactly on the same spot as the other surface, but it's relatively close. And this is why we usually avoid that, but we hope that in the next version of Atom Blend we're gonna have the explicit possibility to do isosurface in here, and then we can do that while preserving the distance, the distance faithfulness, if you will. Okay, so this is one option, and the last option is actually using a really good remeshing tool like instant meshes that we've shown before, and I hope for once now it's not gonna going to die on me. Yep. No, that's not what I wanted. Downloads. Where did the instant meshes go? Now maybe we should extract the instant meshes. Maybe that was the issue, that I didn't extract the instant meshes folder. And now we can go open mesh, precipitate 1. I have no idea what the issue is, why it plays up today. Yesterday I had no problems with instant meshes. But you can get it into instant meshes and use that for remeshing as well. Okay, but we're going to go a step further now, and we are going to mark certain vertices for analysis. We're going to use that merged mesh here, and I'm actually going to delete the original one. No, I'm just going to leave it there. And we are going to mark certain vertices. So I'm going to go back into edit mode, and I might want to have a certain region here that I want to create a proxigram for example. Or later on we're going to create an interfacial access value for. And so I'm going to go Alt A, deselect everything, and then circle select. C circle select, and just create select a certain area on my mesh here. And then what I can do is I can go into the mesh properties, and there I will have something called Vertex Groups. And what I want to do is I want to assign these vertices to a certain vertex group. And we can do that by creating a vertex group first, giving that one a name. I don't know, call it local. We'll call it local, and then I will assign the vertices that I have selected right now. Assign by clicking on assign. I assign them to that vertex group. So now if I go Alt A and deselect everything, and I go on to local and I can go select, and then I have selected that. I can create more than one vertex group, by the way. So I can go Alt A again, deselect, and I don't know, create a second group which is stupidly named local 2, and assign those. And now if I call Alt A, if I go on local 1, I can go select, and it will show these ones. And if I go select local 2, it will show the local 2 ones. So we have 2 vertex groups that we have defined on that object. And now we can export those vertex groups into an OBJ file that we can load into MATLAB. So we'll just go out of edit mode into object mode and go file, export wavefront OBJ again. And data for isosurface, precipitate 1. It's now called precipitate 1 underscore remesh O groups, and it's selection only. We want OBJ groups, and we want Y forward Z ups. And the important thing, OBJ groups, no, we don't want OBJ groups, we want polygroups. So now we need polygroups. So we need no materials, no UVs, no modifiers. But what we need is polygroups. if I export now, can just open the oh no, let's see, we want to go to the data, test data for Isosurface, and now we have that file here. And what you can see now is, okay, we've got our mesh. And then if I move down to here, you can see we have a new type of line in here, which is called G for polygroup. Yeah? And at some point you can see, okay, all of the faces here, they belong to the group local 2. Yeah? And there will be some that belong to the group local and some that belong to the group local 2. And so we now have exported those vertex groups into our OBJ. This thing has one subtlety in there that I need to explain that you actually need to know about. Yeah? And that is that if I go into edit mode and I look at that, I've marked vertices for export, but the vertices for those vertex groups, but we're exporting faces. Yeah? So each face, a vertex belongs to the vertex group is marked for that vertex group. So essentially when we load them in, we also include any of the adjacent vertices that belong to a triangle that one of the marked vertices belongs to. So essentially we're exporting a little bit of a larger area effectively than we have marked here. So if that is a problem for you, one thing you can do is you can refine the mesh. Yeah, so you can refine the mesh, and maybe I'll do that on the other one here. Yeah, so you can go and apply a modifier, and one of the modifiers is a so-called remesh modifier. It's a so-called subdivision modifier, subdivision surface modifier, and oh, now I've applied the modifier to the invisible one. That's obviously not a good idea. Subdivision surface modifier, and now you're actually getting a finer mesh. This is a so-called Catmull-Clark subdivision surface. So this is a smoothing subdivision surface. Essentially, it's a polynomial approximation. But you can also use a simple subdivision surface modifier. So if I go and apply that modifier, then you'll see we have a finer mesh now than before. And now if we mark all of that, we will get a finer resolution with marking. That's why I said creating a finer mesh is always easier than creating a coarser mesh. It's a little bit counterintuitive, but that's the way it is. Because subdividing a mesh is always easier than coarsening a mesh. Okay, so we can load that in again. obj equals obj to patch, but in this case we need another thing here. Yeah? So we need obj and group. Yeah, we need a group variable. Data for Isosurface, and if we load that in now, now we've got our OBJ. In this case, it's again only one object that's in there. But we have an additional variable that we named group. And so now we have two groups, one with the name local2 and one with the name local. And each of those has a list of vertices that is associated with those with that group. And this is the basis of a local proximity histogram. And we're going to see later also the basis of a local interfacial access calculation. So now, well, for proxigram, we had a simple proxigram function. Why did we? And I think I need to just copy the last two commands for you. Okay, so now we can go in a patch create proxy, patch create proxigram. So now what did we call it? So that I can keep using my autocomplete. Autocomplete is great. Alpha allocate. Somewhere up here is our proxigram. Now reconstructions. Okay, sometimes it's just easier to copy everything out of the function definition. So I'll just do it this way. Just go into the function definition, copy it in, and we want to autocomplete all of that. So we want pos dot atom equals, let's use good old aluminium again. Pos, the interface is, oh, we haven't, I'll just do it this way. Oh no, that's actually not, oh, that function actually doesn't include the local proxigram. Okay, so it should though. Fairly sure we've implemented it. Okay, no, we haven't. Okay, but that's, did we, because we will do it through we'll do it through allocations. Yeah, so we're definitely going to implement it on the patch create proxigram command as well, so that they can come in with your Vertex groups and define a local proxigram there. Okay, that's unfortunate. Yeah, again, something to put on our list to update. Sorry about that. But yeah, so what we can do now is then we can go and go bin centers and bin edges, bin vectors from distance, and in this case our distance increment is 1, and our distance is, oh, we need to allocate point create proxigram. Is that the right one? No. Oh, here we've actually implemented it. That is a little bit unfortunate. Okay, so essentially is closest is d search n. So we're just searching which pos which atomic position is closest to any of the, so it's pos dot x, pos dot y, pos dot z, and here we have we first should create the fv dot vertices equals obj dot vertices, and fv dot faces is obj dot objects dot faces. Yeah, so we have defined that, and then we go and find the closest vertex in our POS file to each of the individual vertices that we have collected. Yeah. So in this case, it would be pos.x, pos.y, pos.z, and here we've got fv dot vertices first column, fv dot vertices second column, fv dot vertices third column, and I've been missing some commas here. And now what we get out is a so this is a built-in MATLAB function, and what we get out is an allocation of each one of our atoms to one of the vertices. So this will, for a large data set, this will just take a couple of seconds. I was 100% convinced that we've already migrated that. Maybe I've overlooked that somewhere. By the way, you can also use it pretty easily to split up a data set into individual domains that belong to individual objects. So just imagine you're looking at a data set with the different isosurfaces, and you want the atoms that are closest to one of the isosurfaces. You can mark it the same way. Yeah? And now we've got a list of which vertex in of our interface each atom in our entire data set is closest to. Yeah? And we want only those that are we want only the atoms that are closest to closest to a certain to a list. Yeah, so I'll just call the variable is closest to list. We can just use the isMember function. The isMember function. And if you look into that function, I'll just have to look it up right now as well. Then we get a 1 where the data is of A is found in B. Yeah. So we want to look if our closest vertices are actually closest to a group 1, our first group dot vertices. Yeah. And this is a very fast operation, and we can just count the number of atoms where this is the case. Number of non-zero elements is closest to list. And then we see that applies to about 1 million atoms. That applies to about 1 million atoms. And this is kind of like putting an analysis cylinder perfectly spot on onto those vertices. Yeah? I mean, you can do that manually. You can put an analysis cylinder there, but it's essentially doing that. And you can see it's just a couple of commands, so it's not a lot of work, but that should have been merged in, and I apologize for that. Yeah. And if I now want to calculate the proxigram, I can just go pos in equals pos, our entire pos file. And we only want to use the ones that is closest to list. Oh, I missed one T in all entries. And now we get a variable with exactly those 1 million atoms in there. And we can now calculate a proxigram for those. So we'll go and do it just like we did it before. Oh. Bin centers and bin edges. First calculate distance, and now it's pos in instead of pos. Yeah. Then we can create the maybe I should just make a small function that is called something like pos on vertex group, or pos extract vertex group, or something like that. I think this is probably a good way to do it. Okay, so we want our bin centers and bin edges. The distance is fine again, so we've got that in there. Then we'll create a voxelization now of pos in. Pos in. And our concentration calculation. And now our concentration plot, our concentration profile plot. And there we go. You know, of course, now we have a lot fewer atoms in there. Yeah, a lot fewer atoms in there. But now we've created a proximity histogram only at those vertices. Yeah, so we've created a very, very local analysis of those vertices. And this can so unfortunately in terms of time we haven't done all that great. So unfortunately, unfortunately we won't have time to show it to you on one of the nicer data sets, or maybe we'll just use the last session for that. And then then you should be able to do that. You can also do it on something where it's really interesting, where you see, okay, local I have more stuff, or I have less stuff, and this should give you the ability to dig a lot deeper into your interface analysis than without that. Okay, for the interface analysis, so let's rerun that now with the new interface, where we have gotten rid of all those small triangles. Obviously, now we already had we have updated the interface, so now we can run that. This is obviously the concentration map is a relatively simple analysis to do, and we will update it so that it works with the table-based variables. And I apologize for that, and I also apologize that we haven't actually move the local proxigrams into the analysis folder. Because I'm 100% sure that for the patch create interfacial access, we have actually integrated that. Yeah, so you can select the vertex groups, the vertex numbers there. And for the Blender exporting, so we with add-on Blend 2, we're also going to implement the export of vertex groups, so that you don't have to think about the whole poly group versus vertex group thing anymore. So that you can just mark your vertex groups and then maybe just go and copy the vertices into the either into a PLY file or into into the clipboard, into the clipboard of the computer, so that it becomes very easy to export vertices and meshes from Blender, including vertex groups, without having the poly group issue. Okay, so now that's the updated map. And of course, in this case, I apologize, it's not that interesting. There's not that much change. You can actually switch on the legend, the color bar, so that you can see. Okay, it goes from 0.4 or about 4% to about 16%, and most of it is kind of in the middle, which kind of makes sense because we used a 7% aluminium isosurface, so the concentration of aluminium on that isosurface should be, well, 7%. And that's roughly what we're looking at. Yeah, most of it is in sort of this color tone here. So yeah, it's kind of what we would expect. You can, by the way, export all of that. Yeah, so you can export all of that into Blender, including the colors, by using Patch to PLY. Yeah. Patch to PLY. And now we're exporting, if you have an object selected, which I have, so I have this object selected. We can go Patch to PLY. So PLY is a different export format. It's also a polygon format. It's actually a Stanford polygon format. We'll just call it aluminium 7% isosurface concentration map. And it's the aluminium concentration map on an aluminium isosurface. Yeah. And we can save that. Oh, and I should have, okay. So I missed to copy this function over into the new toolbox. So that goes onto the pile of things to do as well. So have I copied everything over? Yeah. Okay, sorry that there were a couple of issues, but we are going to resolve that, and we're going to merge that into the toolbox in the next coming days, because these are all really minor things. Being able to select vertices when you create a proxigram, yeah, stuff like that, or being able to split your data set up by vertex groups. These are all really minor things that are really don't take a lot of time to implement. Okay, but with that, we are at the end of this part of the session. So I really hope you now understand how to create local proxigrams, and in the future, we'll obviously make it a little bit easier. But you should have understood by now how it works. So you can go and mark certain parts of the surface, and that you can go and calculate concentration maps of isosurfaces of any analysis objects that you have created. Okay, and with that, we're going to go into a 15-minute break, and I'm going to stop the recording again, and you can ask questions if you want in between. You still have 20 people, so that's pretty good.